Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the Ampere circuital law. So you can see that in this Ampere circuital law, it says that the line integral of magnetic field. This is the line integral of magnetic field around any closed loop is mu naught times the current passing through the region bounded inside that loop. Now this complete quantity B dot dl integration is called as circulation on a closed loop. So we can call it as circulation, and this circulation is equal to mu naught times the current passing through the region inside the loop. Now according to this, you can say that in this figure, if this is a loop, Amperian loop, and there are three currents which are linked with this region inside this loop, so we can say that integration of B dot dl we can write down as integration B dot dl is equal to mu naught times now first of all, we see that we always calculate the integration, this circulation, by Fleming's right hand screw rule. So if you are considering this current which is coming out of this plane to be positive, then you can point your thumb in the direction of the current, and then you can circulate the fingers around this thumb, and you will find that fingers will be circulating like that. Okay, so you can write down that this complete B dot dl will be equal to I1 plus I2 minus I3. Now it does not matters that I1 is obviously perpendicular to the plane, but in fact I2 is perpendicular to the plane, but I1 and I3 are not perpendicular to the region bounded in the loop, and it does not matter that currents are perpendicular or not. The only thing which matters is the fact that currents are should be linked from the region inside the loop. Now this is, you can see the right hand thumb rule, and you can we will be calculating the electric field or magnetic field due to a long straight current carrying wire, which we have already calculated by Biot-Savart law previously. So we will be calculating that field by Ampere circuital law. But before that, let us discuss some more important points of Ampere circuital law. So the first point states that the circulation of the magnetic field is independent of the shape of the loop around the current. So obviously this B dot dl is mu naught I inside for this loop also, and this is integration B dot dl mu naught I for this loop also, and for this loop also it is B dot dl is equal to mu naught I. So for all these three loops, irrespective of their shape, this is valid, as well as you can see that this current carrying wire is passing through the center of this loop, but this wire is not passing through the center. So this is also valid. This circulation is mu naught I inside for all type of wire placements, irrespective of the fact that wire is symmetrically placed or asymmetrically placed. You can see that in this case wire is asymmetrically placed because the points on this Amperian loop are at different distances from this wire, and in this case wire is symmetrically placed because the points on the Amperian loop are at equal distances from the wire. Okay, so Ampere circuital law is also valid for any shape of the loop as well as for asymmetric wired current distributions also. Now Ampere circuital law is not valid for calculating the magnetic field generated by the time varying electric field, for which magnetic field for those magnetic fields Ampere Maxwell law is the valid law which was given by Maxwell. So what I am trying to say is the fact that this magnetic field is which we are studying is being generated by current carrying wires, and you will study in the further electromagnetic waves that time dependent, time varying electric field also produces some magnetic field. You will be studying in that chapter. So for those type of magnetic fields which are created by time varying electric fields, Ampere circuital law becomes invalid, and I will show you how that it becomes invalid in EMW chapter. But at that point, Maxwell suggested a change in this law, and he named a new law as Ampere-Maxwell law, which we will study in electromagnetic waves. Okay, so this law is valid only for the magnetic fields which are created by current carrying wires and not by the time varying electric fields. Now, the circulation of the magnetic field around a closed loop depends only on the current passing through the region bounded inside the loop and not on the current passing through the region outside the loop. Obviously, when we will write B dot dl for this situation, this one B dot dl, then this B dot dl will be equal to mu naught times of I1 and I2 only. There will be no inclusion of I3 because this is not passing through the region bounded inside the loop. But this is very interesting and very important to note that if we are calculating the magnetic field at this point, then you can see that if you remove the loop and you will be finding out the magnetic field at this point B, then obviously you will say that at this point all the three wires will be creating magnetic field, not only these two wires. This is obvious. So we cannot say that the magnetic field at this point on the Amperian loop will be due to the current which are bounded in the loop. This is wrong, and therefore we can not find out the magnetic field at this point by using Ampere circuital law for this situation. So when the wires are asymmetrically placed, let's say that in this case there are two wires and the point B is at different distance with these two wires, and obviously one more wire is kept at this point, and if in any other case a wire is passing through a region that is not symmetrically placed with the loop, so this point is at a lesser distance from the wire and this point is at a greater distance from the wire. So we cannot find out the magnetic field at any point of the Amperian loop by using Ampere circuital law. But obviously we will not say that Ampere circuital law is invalid, because Ampere circuital law does not tell us about the magnetic field. It tells us about the circulation of magnetic field, integration B dot dl. And integration B dot dl for all these three kinds of placements, wire placements, is valid. This is valid for this one and this is valid for this one also. But we cannot find out the magnetic field by using Ampere circuital law for asymmetric wire distributions. So I think you have got the point that we cannot find the magnetic field by using Ampere circuital law for asymmetric current distributions, but this doesn't mean that Ampere circuital law is invalid for asymmetric current distributions. It is equally valid, but we cannot find out the magnetic field, okay, by using this law for asymmetric current distributions. Now again, this is the same point which I have already stated, that we cannot, as Ampere circuital law tells us about the circulation of magnetic field, and hence for asymmetric current distributions in the Ampere loop we cannot find out the magnetic field using Ampere circuital law, but we can find out the circulation of magnetic field around that loop. So obviously for this loop we can write down integration B dot dl is equal to mu naught I, but we cannot find out the magnetic field through this loop, through this law for this loop. This would be not valid. So this was the complete Ampere circuital law, and now we will be finding out to prove the correctness of the Ampere circuital law, we will be finding out the magnetic field generated by a infinitely long wire. So you can see that this is an infinitely long wire which is carrying a current I, and to find out the magnetic field at this point P, I have assumed a circle which is centric at this point, which is lying on the wire, and P is on the circumference of this circle. So if we write down integration B dot dl, then it would be equal to mu naught I, which is the current passing in the loop, and the limit of this expression will be from 0 to 2 pi r. And obviously the direction of magnetic field and the direction of dl are parallel to each other, because they both are given by Fleming's right hand screw rule. So B into 2 pi r is equal to mu naught I, and B will be equal to mu naught I by 2 pi r. This is the magnetic field due to the infinitely long current carrying wire, and we have already discussed this field previously by using Biot-Savart law. So this was the complete Ampere circuital law and its important points, and in the next video we'll be discussing the different applications of Ampere circuital law. Thank you.